Yeah, very good afternoon to everyone. So this is the topic of my presentation. I'm audible, right?
Yeah,
Am I?
it's
Yeah,
perfect.
yeah,
We can
thank
see
you.
your presentation.
Yes. So the title is Interaction and Inhibition of Alpha Glucosidase with Selected Monoterpenes. So it has been estimated that 425 million people are suffering from diabetes, and 90% is type 2 diabetes. And World Health Organization claims diabetes will be the seventh cause of death by 2030. So many of these shocking figures emphasize to look for some inhibitors of glucosidase enzyme. So here there are synthetic alpha glucosidase inhibitors that are available. For example, acarbose, which is a popular one, which is used as anti-diabetic agents, but they do have a lot of side effects, including diarrhea and flatulence. So for this reason, so we can go for an alternate, right? Some phytochemicals, some natural compounds. So that's the purpose of this study. So there are many reports on monoterpenes as inhibitors of glucosidase. So just we wanted to identify the structural parameters which contribute to the functionality. So there are many enzyme inhibition studies are actually done on monoterpenes, but monoterpenes extracted from plants, which is in the form of essential oils, right? They are not individual compounds. So hence the present study aims to analyze the inhibitory and interaction potential and through a structure activity relationship of selected monoterpenes against this enzyme, alpha glucosidase. Okay, so we extracted maltase from a eukaryotic source from yeast, especially Merozyma guillermondi. So that's the organism which we have used. And we used YPD agar, yeast peptone dextrose agar for cultivating the particular yeast. And then we have extracted this enzyme maltase. And then we verified whether this is having a alpha glucosidase activity by dinitro salicylic acid assay, the classical biochemistry test. And then the maltase inhibition assay based on the UV visual absorbance and at this wavelength. And then we identify the IC50 values from the slope we plotted from these values. And then we have prepared the ligands. These are monoterpenes, which were used using this LigPrep module of this Schrodinger software. And then we have developed a 2D QSAR modeling equation, right, based on auto QSAR tool of Schrodinger. And then we have done a molecular docking with human maltase, because ultimately we are looking for anti-diabetic effect. So there's a crystal structure available from PDB of human maltase glucoamylase protein. This accession number was used, and we did all these preparatory addition of hydrogens, and then the polarity aspects. All these are taken care using this grid based docking protocol, glide. And this is a crystal structure that's available. I mean, this picture is actually taken from the PDB 101 website. So you could clearly note there is an N-terminal domain and there is a C-terminal domain, and the catalytic domain, which is there in the middle, and the active site is enclosed in the box, wherein you could see the it's already complexed with this drug acarbose, which is an anti-diabetic drug. So that is already complexed right in the center. So since it is having some side effects, so we wanted to try out with some monoterpenes. So we just the extract which we have got it from the yeast, we just wanted to try whether it is having alpha glucosidase activity, and we have used this paranitrophenyl glucoside substrate, and the paranitrophenol, if it is eliminated, that will give this color, yellow color. So this gave an yellow color, so that indicates that it is having a alpha glucosidase activity. After confirming this, we just also verified with the UV visual spectrophotometer, where there is a clear deflection in the peak. There's a peak shift with the enzyme inhibitor. And without enzyme inhibition, it is the peaks were different. And with enzyme inhibitor, I mean, it's total shift. So similarly, there are for other compounds shown for the alcoholic version of citronellol, and then aldehyde version, citronellol. And then we have computed the IC50 percentage based on the slope obtained from these points at different concentration. The concentrations were mentioned in the previous slides. So it's a 0.11 micromolar, 0.22 micromolar, 0.33 micromolar, and so on, right? And these are without enzyme, and the same with enzymes. Okay, so based on these plots, so we have derived the IC50 values for each of these selected monoterpenoids like camphene, 1,8-cineol, cinnamic acid, and so on. So the overall IC50 value, which is the logarithmic scale we have expressed here using the PIC50. So these are the compounds which we have taken. We have developed a QSAR model, and there were some outliers. Some compounds were outliers, and again, depending on the training set and the test we have used. So we have used a training 80%, and then we also included some new compounds to this 20% for testing. And then we have performed, I mean, based on the experimental inhibitory assay, we just wanted to verify the structural interference. So we have chosen this acarbose as a standard, the control for the experiment. And you could see there are a lot of interactions with acarbose, right? A lot of hydrogen mediated interactions and some hydrophobic interactions. So this was set as a standard for comparing other monoterpenoids. So carvacrol, so there is a hydrogen mediated interaction, as well as the phenylalanine and tyrosine residues of the glucoamylase also had a pi-pi interaction, pi-pi stacking, because these two are aromatic amino acids. So this aromatic ring, it was having a pi-pi stacking kind of interaction. And then carviol had hydrogen bond mediated interactions, because there were a lot of OH groups. And then citronellol, the aldehyde part of it, just have a hydrogen interactions, just one single interaction. And then citronellol, it's also having one single interaction. And then p-cymene, it's having a pi-pi interactions, right? And then thymol is also having a pi-pi stacking interaction. And then 1,8-cineol. So some of these are not having hydrogen bond mediated interactions. They do have a hydrophobic interaction. So for example, this 1,8-cineol is having just a hydrophobic interaction. Alpha-pinene is also having hydrophobic interactions. And then limonene is also having a hydrophobic interactions. Yeah. And then based on the, I mean, these are results after docking, but these are the scores indicating the amino acid contributions, the atomic contributions of the ligand, say for example, so acarbose, the oxygen 16 of the ligand is interacting with asparagine 207. So that's expected to be in the binding site. And then oxygen 17 of the ligand, it's interacting with 309. And again, aspartate 327 with oxygen 16 and so on. So all these are the interactions with the amino acids in the active sites shown here. But see, acarbose is the standard drug, anti-diabetic drug. That's having a very minimum score in negative terms. So it's more stable. This is more stable compared to all other monoterpenes. But there is a scope because almost all these are in the similar range. But I mean, we need to do some modification so that like um, we can make them equivalent to acarbose in terms of inhibition. So except like few like citronellol, and 1,8-cineol, so they are having high docking score, but whereas these set of compounds having a low docking score and having very good interactions too. So this can be taken up as lead for further anti-diabetic drug development. So this is what we hypothesized from this. So from our results, monoterpenes interacted with maltase or glucomylase and had an inhibitory effect for sure from the wet lab, as well as the in silico analysis. But the ligands such as carboxyl, carviol, citronellol have hydrogen bonded mediated interactions, whereas parathymine, thymol had pi-pi stacking with tryptophan or phenylalanine or tyrosine with these three amino acids, and 1,8-cineol, alpha-pinene, and limonene. So only these three had non-bonded interactions. So, but the binding energy of the around 10 monoterpenes which you have taken, and so that is varied from minus 4.9 to minus 1 kilocalorie per mole. So the energy, binding energy, there were differences. And again, which can be contributed by the bonding or non-bonding kind of interactions. And acarbose possess the lowest binding energy, right? So none of them are equivalent to acarbose, but in order to come out of these side effects, so we need to look for more alternatives, right? So that's our idea. So we need to look for more alternatives. So we have restricted only to monoterpenes. Maybe we can add on some triterpenoids and check whether they are of use, like inhibiting these maltase glucomylase. So hence the search for novel ligands from natural source. So we cannot conclude anything from this. So we'll continue. So we need to continue this to find a better lead for further anti-diabetic drug development. Okay, so that's it. So these are the references used. And yeah, thank you very much for the opportunity.
Thank you very much. I see one question in the chat.
Okay.
From Kunai Rao. It was not clear which descriptors were used in two-dimensional QSAR study and how the quality of the model was determined and how the model was interpreted.
Okay, I mean, we do have computed around 800 descriptors, but the most significant ones are the usual ones like the log P, and then the hydrogen donors, hydrogen acceptors, the number of rotatable bonds, and the chirality and the topology related descriptors. Yeah, I have not mentioned those. Yes.
Okay, thank you.